in NP. So that is our forever x in NP right there. That means that there is a non-deterministic Turing machine, we call it N, that decides x in polytime. That's what that means. That means that if you have some string in x, then there is a computation history of n on w that ends in acceptance. That's what it would mean for n to accept w. And if n is a decider for x in polytime, that means that whenever you feed it a string that belongs to x, n will accept it. It also means, so that's the computation history I'm talking about. That's a computation history, it's a sequence of configurations. So you have initial configuration, you have another one, eventually you'll end in accepting configuration. Alright, there's more than that though. The fact that it runs in polytime also means that there will only be a polynomial number of those configurations in getting to this acceptance. Right? There's a computation history that ends in acceptance. Maybe I'll just tack on the and rather than try right. And it is at most p of the length of w steps for some polynomial p of n. Okay? In other words, if you say that the Turing machine runs in some polynomial of the input size, I don't care what our polynomial is, but we could write that down. It's an upper bound on how many steps it takes, and it's fixed. We know it. So here's the plan. To construct f, what you're going to do is, given a w, remember f takes in w. What f of w is going to be, this is where it gets slightly ridiculous, but it's going to work. F of w is going to be this massive Boolean formula that effectively, if the Boolean formula were true, it would mean that you would have found the computation history that has this property. It starts with the right string, ends in an acceptance, and doesn't take, it's a legitimate computation history, and doesn't take more than p of n steps. How does that work? What we're going to do is pretend that the computation history was written out, like in monospaced font. So each configuration would be a string. It would have a maximum width, right? But if you can't run in more than polynomial time, that means you can't write more than polynomial numbers characters onto the tape. So the amount of time you have is maximum width of that configuration. So if I imagine you write it out in monospace font, then the history of going from start configuration down to an accepting configuration actually would kind of look like a big table. And I'm writing in characters, and the characters would be the characters from the tape, and of course state. And I would start from the initial one, and each row of my table would be the next configuration. So we call it a computation tableau. well, I need to mention that f is based on n, so let me just insert that. Say it's satisfied. If not, then not. Oops. All right, can I just say, if I know live, okay, I can just say the converse. Okay, so let's talk a little bit about so the output of f is this big Boolean formula. Now let's talk about what the variables represent in the Boolean formula and how it's constructed. All right. So the idea, I want to draw the construction, or at least describe it. But I'm trying to see. I think I need one more sentence for this all to make sense. You're gonna consider computational history would look like. And define a variable for every symbol in that history. Okay, and if you're treated it as if it's in this monospace font, then all the characters across would line up in columns, and so basically you'd have a big table. So row 1, which is configuration 0, initial configuration, will just occupy the top row of your table. And then the next row would be the next configuration that non-deterministic machine would have taken on input W. And the next row will be whatever next configuration it would have taken. If you write them out in this monospace font, you could literally think of it as this big table that you're just filling in the boxes in the table with the cells or with the elements of the configuration. Okay, that's what we're calling the tableau. All right, so we're gonna set up the tableau in such a way. We're gonna set up F's output to have little markers for the edges so that we can write the correct logic for all the pieces that we need. Alright, so we already know P we know P, so given W we can figure out what P of W is. describing a tableau of cells. So represents that is P of W plus 3 cells wide and P of W, I guess, plus 1 rows high. Alright? The edges, so the left and the right of each row, contains that special symbol, which we'll just use like a sharp sign, which must not have been a part of the alphabet for X. It's just meant to be a sentinel value. Alright, let's take a look at one and draw some pictures. So that is going to be like this. A big table where I have these pound signs going down on the left side, and I have pound signs going down on the right side. And what's written in each row is a configuration. Now the initial configuration, of course, is going to be, if it's a valid configuration to start, it would have to be the start state followed by the input on the tape. So the initial configuration always looks like start state followed by W, right? So you'd see the very first one would look something like Q0, or Q0 is the start state of N. You know it because you have N, W1, W2, Wn, where that's what this W is. You got W, so you know the characters are W. And then the rest of these, of course, are just blanks. So that's what the initial configuration would look like, right? Now, we're not gonna actually output that string. We're testing for that string. Rather, what we're outputting is a formula that will check whether this is actually the case. So let's talk about the conditions that we need. So we need for, so the requirements are, well, let me see. Before I get into the, okay, I won't write down the requirements, I'll just tell you where this is going. Remember that we're trying to capture a formula to represent this picture. And when I say what this picture is slightly incomplete because I haven't said the rest of it. What am I trying to capture? I'm trying to output one formula that's gonna, in all its glory, say there is this tableau. The first row looks like this. It has legitimate entries in every cell. The step from one row to the next is a legitimate step that N could take. Transition, exactly. That somewhere down here there's an acceptance, because it must accept. And what else? So we have legal move, we have right start. Oh, that every cell has a valid symbol in it. So 4 criteria we're going to want to say. So we have that the start looks like the initial configuration. That, so okay, that I can write down because I'm working on time. So so the output of F is actually a Boolean formula that will capture this idea. The output of F. So this was an illustration of what we're trying to test for. So the output of F is a Boolean formula. Each variable represents a cell. I'm going to be like this. So X, I, J, S is going to, so if this is equal to a 1, if this is true, means that cell ij contains S. For some S in, which I'll just call C, which is going to be, what's the C I'm talking about here? It's going to be the alphabet, the tape alphabet of N union with Q. Remember when you write down a configuration, there's a state as well as tape symbols. And we're going to throw in the sharp as well. Sharp must not have been there before. So basically, the C is just a set of all possible characters that could appear in this tableau. Okay? So this is what a variable looks like. It has 3 subscripts. Remember, the variables are only true or false, but they're Boolean variables. So in order to say that, we can't do like what you might do in coder. You might say cell ij is a character and store the character in there. Rather, what we have to do is create a different Boolean variable for every possible combination of characters and coordinates that it could possibly be. And just think about it. How many coordinates do I have going across? This is what is going to be P of W plus 3 going across here. And the reason it's plus 3 is that it's 2 sharps and the Q. Right, the maximum width of the tape could have been P of W, whatever that polynomial is, so the extra 3 characters is the whole of configuration. And this height is at most P of W. I said plus 1 because I guess you start here, maybe you can take P of W steps, so you're going to have one more row at the bottom.
As you said, the width completely.
Right. Right, so that is the picture we're trying to form, trying to represent that with Boolean formula. So, these are our variables. What do these clauses look like now? What are the constraints? So each variable represents a cell, and we're gonna have 4, so we're gonna have some really complicated clauses, but the clauses are gonna cover by 4 main constraints that have to be satisfied. So, f of w is equal to phi, like a big phi, which is going to be the and of, let's do it like this, phi cell, so we'll talk about what it means to be a legal cell, and phi start, which is going to set the constraint for how you must begin, and phi move, let's call it that, which is going to define what it means to be permitted, what's the legitimate one row to the next, and phi accept. So these are sub-formulae of phi. Okay, where? We have to back over this. Phi cell is a formula insisting that all cell variables are legal or consistent. I say that. What does that really mean? So for example, it means that among all of these, one is true. Yes? You must have some symbol in each cell. And you're not allowed to have any two of them being true. So phi cell sort of looks like, okay, one big R over all possible IJS. We need that one is true, and for all the I think I'm missing a piece. Okay, what do I say? No two of them can be true at the same time. So for all IJ, yeah, but I have to write that using only ands and ors. The exclusive are over all. So for each, I could probably get messed up if I try reconstruct it in a hurry, which I'm already over time, and I want to show at least what others kind of look like. So let me abandon this and leave it like that. But just to give you a gist of how it would look, it would be for any cell ij, right? So you have this iterated loop that says, and it's and over all the ij because it's true for every ij, right? But within a particular ij, exactly one of the symbols is present. So you would have xijs true, and then for every possible pair of S and T, where S different from T, S and T being two symbols, you don't have both of them be true at the same time in the same IJ. So that's kind of what I was trying to write here. Okay, for every IJ, you have one. I guess I'm writing this again. So what am I missing? So this is for over all the S's. One of them is true, and no two of them are true. So, and for S not equal T, S and T in C, XIJS is either that or XIJT. So if you take all possible pairs of symbols, one of them must be false. I think that would cover that no two of them could be true at the same time. And then one of them has to be true across over all symbols. This is, so what I'm trying to say here is that each cell contains exactly one symbol. So forgive me if I get the logic, the Boolean logic wrong, but I hope you can see that there is a way to write this down. Right? Even if I got this wrong. And I'm trying to say here that every cell contains a symbol, but I think I may have botched that slightly. Alright. So that's what we mean by legitimate cells. So this basically just says, okay, because remember every cell is just a variable. And it could be independently true false without putting these constraints in. So this constraint is trying to say every cell has exactly one symbol. So that means you're not supposed to find Xij for two different symbols being true at the same time. For the same I and J, two symbols can't be in the same cell at the same time. That's what this is trying to do. And every cell contains it exactly. Every cell contains at least one symbol, and no cell contains more than one symbol. That's what we're trying to say. Okay, what does phi start look like? Phi start actually is easy. Phi start says that the first row looks like this. So phi start actually literally would be that x1, if I started indexing from 1, x11 sharp. And so that one I can write down here. Phi start is x11 sharp and x11 1 to Q naught. Oops, that Q naught kind of big. It's supposed to be a subscript. And X13W1 and so on. That makes sense? That's just one big sentence that's saying row 1 looks like this. And that's a big and of these variables, yes? Okay? So that's what that Boolean form looks like. If I move now, and this one gets complicated. But the way that this is built is you look at slices of 3 across and 2 down, so 2 by 3 windows. And what you do is you look at the transitions in N, and you enumerate all possible legal 2 by 3 windows. And put those together as big ORs. That's what find move looks like. And then finally, if I accept, that one's not so hard. That just simply says there is some I somewhere that contains QA, Q that accepts state. So there's some I, some J somewhere that contains Q accept. So phi accept is there's an OR over all IJ because we don't know. We don't know where it might appear. That X, I, J, Q, A appears somewhere. Because for once the machine enters Q, accept state it accepts. Okay? So you see that it's a huge Boolean formula, but it's still a Boolean formula. Now what does it mean? If you could satisfy that Boolean formula, that means that you found a way for this to be true, for this to be satisfiable. There's a way to assign true false to all the Boolean variables, which of course is Boolean for them is P of W plus 3 times P of W1. So like P of W squared times the size of this set. That's how many Boolean variables we have. Yes? But guess what? It's still a polynomial. Because this is fixed, it's a constant. It's still a polynomial in W, it's just a polynomial in W squared. So the size of F is huge, but it's still a polynomial in W. What do we do though? We built a huge massive Boolean formula. Now let's see, suppose you could make it satisfy. If you could satisfy this, because this is an AND of all these 4 clauses, that means you have to satisfy all 4 things simultaneously. Which means what? That it's a legal, every cell is legitimate. The moves are actually representing what N could do. The start in config was the initial config that it should be with the N operating on input W. And somewhere there's an acceptance, which would mean that N would have accepted W. And you can go the other way, suppose N would accept W, well then that means that this tableau does exist, which means that there is a way to set the Boolean variables to true or false to make the whole thing be satisfied. So there we have our if and only if. So the Boolean form is satisfiable. It means that there was an accepting sequence or accepting computation history. And the other way, if N did accept W, that means there's an accepting computation history, which means we could write it out, which would tell us what the variables should be, which should then give this Boolean formula a way to be satisfied. So hence, it just proves, or well, that's how Cook-Levin did it, basically just demonstrating that take any problem in NP, it is possible to reduce it to SAT. So now, if you had a polytime solution to SAT, technically there is a polytime solution to that NP problem. Notice that this reduction doesn't tell you how to solve that NP problem, because this reduction depended on n, and if you don't have n, that means you can't legitimately construct this explicitly. You kind of have to have n to do this construction. So that doesn't give you an algorithm, but it tells you that if you do have a language in NP, it is possible to construct this mapping reduction in such a way that this is an if and only if relation, so it's a polytime mapping reduction, which means that it is reducible to SAT. Okay? So upshot, SAT is NP hard. That's the takeaway. If you don't remember anything else, that you need to know. How it works, why it's true, that's gravy. Okay? I'm not gonna ask you to regurgitate this. Now here's the thing though. What happens when you have to prove your own problems NP hard? Are you gonna have to get creative like this? Are you hoping you do? You should be hoping you're not. Because this is like out of this world. Like, how does somebody come up with this? So the good news is that you don't have to come up with this. The next class we're gonna talk about some techniques. Well, it's not techniques, it's examples. I'm gonna illustrate various examples for proving different problems being NP hard. This is the stuff of that book I mentioned by Gary and Johnson, and somebody, I think it was Renee, somebody asked about, they call somebody's name. I don't remember his name. Huh? They included a third guy in Cook-Levin. I think that's the name I recognize as being the one who did the graphs, which is what we're going to talk about next class. You don't remember his name? I actually can't remember. Anyway, so the textbook that we use attributes this proof to Cook-Levin. The body of work that builds on top of all this NP hardness, proving all these other languages NP hard, a lot of what comes, like the techniques that we use practically come from the work that came after. So like this is just to establish that something does exist. But the real kind of insightful, really seminal piece of work was when, as I said, I don't remember his name. When the name is called, I remember seeing it in that context. But Gary and Johnson produced a book. It's a big book. But I think before they published that book, there was this bit of work that showed, look, take a graph, ask, does it have a clique of a certain size? Can you color it? Does it have a Hamiltonian path? And it turns out that many of those problems you can reduce from SAT. So you can reduce a Boolean formula to those graph problems, which means that if you could solve the graph problem, you could solve the Boolean formula problem. And so then therefore those are NP hard as well. And it was this neat network of related problems that then kind of created this explosion, because suddenly these graph problems are so general, many other problems could be mapped to those graph problems or reduced from those graph problems. So you prove the graph problem NP hard, and suddenly these other problems are even harder than them, which are everyday problems like scheduling and timetabling, and, avoiding collisions, and trying to efficiently dispatch shipments, and those kinds. Knapsack problem, all these kinds of problems are actually representations of real life problems that turn out to be NP hard. So that's what we're going to look at in the next class. That's tomorrow. This class is wrapping up very rapidly. I don't know what's going to happen because Easter kind of threw out the intervention or Isn't Friday, Good Friday on Monday? So, yeah. Which one? Wait, no, where? Or where? Here?
I understand why it's on, but isn't the CNF supposed to be R? It's like a proof of R.
Oh, right. But then each one counts as a clause. So this is like a clause with one variable in it, and another one, and another one.
Okay.
This is not tree CNF, you know.
Oh, okay, so you're saying that not x11 star is like checking every single symbol in XX1.
No, X11 sharp is asking, is the sharp symbol in cell 11?
Yes, sir, but it would look like X11 with all the symbol and the X11 sharp would be true.
The formula itself looks exactly like this. This is literally the formula. The only thing missing is the rest of it.
No.
The truth assignment, there are other variables. There's X11,
Yeah, that's what I'm saying.
A0, so on, yeah.
So that is what?
But it's not for us to set the variables though. That is for the sort of conversion. F only
So
outputs a formula.
So this, what would be there instead of X11 star would be the bracket with the R.
There's no star.
Sharp, sorry. It would be the bracket including that with the rest of the symbols in C, right?
No, that is my literal formula for 5 stars.
Yeah, I understand that.
I don't have any other missing pieces. There's no bracket with anything else missing for the 5 star. So I have no 5 star does not impose any constraints on the other possible values of x11, 0, x111, all other possible symbols that could occupy here. 5 stars is not what imposes those. It's going to be 5 cells that makes sure you couldn't have put anything else. If 5 star says x11 must have a sharp in it. 5 cell says no cell can contain 2 symbols. So there'll be no S as a given ij, so that's 1, 1. There'll be no 2 symbols, S and T, that are both true at the same time. So this is where the constraint that prevents you from writing more than 1 symbol here happens. If that's what you're trying to get. And if you just look at the syntax of whether it matches CNF or not, if that's what you're asking about, this is already in CNF because this is a trivial clause of only 1 literal. That's what I was trying to say.
It's already in CNF because what?
This is a trivial clause of only 1 literal in it.
Oh, okay.
That's what I'm trying to say.
Oh,
That's what I said first.
Okay.
Because it's not 3 CNF. If it was 3 CNF, I would need a triple. It's this, just 1.
Okay.
Yeah. Alright. So tomorrow? Tomorrow we'll look at some proofs for